Spin, the term for intrinsic angular momentum of an electron. It's also called the up or down. If we transform the conventional computer logic from zeros and ones to up and down, it would be a groundbreaking evolution in processing for computers. A research team at University of Cambridge aims to do just that. But how? They've actually found a way to use light particles as a switch. This switch can connect and control the spin of electrons, making them behave like a nanomagnet. This transformation allows for electrons to be applied in quantum applications. So that we are able to apply these magnetized electrons to quantum physics, the researchers needed to develop something totally new. That's when they came up with the design for a modular molecular unit, which creates a micronized bridge between those units. When light is shined onto that tiny bridge, the electrons on the opposite end of the structure connected with one another, thus aligning their spin states. So as far as quantum properties are concerned, this type of control is usually only achieved at an ultra-low temperature. However, this Cambridge team of researchers managed to control this behavior of the materials even at room temperature. So now that it's possible to reliably couple spin to photons, what does this actually mean for quantum studies? Well, hang on tight because soon you'll know. Nearly every type of quantum technology in existence is based on the strange behavior of particles at a subatomic level. When electrons move, they typically form stable pairs, where one electron spins up, whilst the other spins down. But you might be wondering, is it possible to have a molecule with unpaired electrons? Well, in short, yes, it is. They are called radicals, and most of them are very reactive. And with very careful design of a molecule, they can be made chemically stable. So when unpaired spins occur, this changes the rules for what happens when a photon gets absorbed. Electrons will take on a higher energy level. According to Sebastian Gorgon from the Cavendish Laboratory at Cambridge, they have been working with systems where there is one net spin, which makes them good for light emissions and making LEDs. Gorgon is a member of Professor Sir Richard Friend's research group. They've been studying radicals in organic semiconductors with the intention of light generation. They identified a stable and bright family of materials many years ago. These same materials leave the best conventional OLEDs in the dark when it comes to red light production. This achievement was unlocked by implementing strategies taken from different fields of study. This research was led by Dr. Emrys Evans of Swansea University. His team specializes in areas of physics and chemistry, with a special focus on spin properties of electrons and how to make LEDs work with organic semiconductors. This was a vital aspect of the research to know how to approach the use of the molecules in solid state. Essentially, it enabled the team to demonstrate quantum effects at room temperature. But before moving forward, what is an organic semiconductor, and why does this matter? Simply put, organic semiconductors are the pinnacle of technology today for lighting and commercial displays. They could provide a more sustainable alternative to silicon for solar cells. But they have not been extensively studied in quantum applications like quantum computing or quantum sensing. So, a massive step forward and breakthrough has happened with the link of optical and magnetic properties of the radicals in organic semiconductors. This opens up an entirely new application, now that the need for ultra-cold environments has been eliminated from the requirements list. But make no mistake, it is not a simple task, especially at room temperature. Because of the change in temperature parameters, a whole new approach to control the properties is needed. That's why the researchers designed an entirely new family of materials based on how they wanted the electron spins to behave. The result? The bottoms-up approach, which then allowed the control of the properties at the ends of the materials using a building block method, thus changing the bridges between modules of the molecules. The bridges had to be special, and that's why the molecule of choice, anthracene, was chosen. It's a type of hydrocarbon. The researchers then attached a bright light-emitting radical to an anthracene molecule. After a photon of light was absorbed by the radical, the excitation spread to nearby anthracene. This caused 3 electrons to begin spinning in the same manner. When a radical group is attached to the opposite end of the anthracene, its electron also couples, bringing in a total of 4 electrons spinning together. With this illustration, we can effectively switch on the interaction between 2 electrons on opposite ends of a molecule by simply aligning the spins of electrons on the bridge that is absorbing a photon of light. The electrons, remember, they were spinning together even after the bridge is removed. To sum this up in just a few seconds, absorbing a photon is effectively turning on a switch for the electrons to couple their spin, allowing us to reliably control the quantum objects at room temperature. It is important because people have been trying for years and years to do this, and it was made possible by taking the bottoms-up approach in the design method. And now, specific molecules can be designed for spin alignment based on that model. Professor Sir Richard Friend calls it the Goldilocks zone, where you can tune the spin coupling between the building blocks of extended molecules. Of course, not all the credit goes to one man or institution because the materials were made in China. Experiments were done in Cambridge, Oxford, and Germany, and theory work was done in Belgium and Spain. This research was supported by the European Research Council, the European Union, the Engineering and Physical Sciences Research Council, part of UK Research and Innovation, and the Royal Society. Richard Friend is a Fellow of St. John's College, Cambridge.